Chapter 4 Entropy Section 4.2 The Carnot Cycle. The Carnot Cycle consists of 4 reversible steps. In each step, P external is equal to P. The Carnot cycle is a process undergone by an ideal gas. So here we have the diagram for a Carnot cycle. It involves 4 steps: the red one, black one, blue one, and black one. 4 states are involved in this cycle. They are arbitrarily labeled 1, 2, 3, 4. But we're gonna study these 4 steps from state 3. So from state 3 to state 2, it's isothermal expansion under a constant temperature condition. And temperature is denoted by TH, T hot. From 2 to 1, it's adiabatic expansion, volume increases. Adiabatic means Q is 0. And then we go from 1 to 4. It's isothermal compression because volume decreases. And in this compression, temperature is again held constant, but this temperature T sub C is different from T sub H. T sub C stands for T cold, lower than T hot. Finally, we go from 4 to 3. It's adiabatic compression. We get back to this original state. So we can go from this state 3 and then 3 to 1, 4, 3. Alright, we're going to look at all 4 steps, and we will compute Q, W, delta U, and delta H for all steps. And we'll see after this Carnot cycle, delta U and delta H should be 0 because U and H are state functions. However, Q and W are non-zero. Now, what about entropy? Well, delta S is also 0 because entropy is also a state function. So we're going to do some calculations, some derivations in this section. First, let's look at this isothermal expansion from state 3 to state 2 at this temperature T sub H. Actually, it's just T hot. Because this is expansion, work should be negative, and we can derive the expression for work. Work hot is equal to negative integral P external dV. The reason I put P here is because all 4 steps are reversible steps. Therefore, P external is equal to P. And we integrate this from the initial state 3 to the final state 2 in this isothermal expansion. And pressure is nRT over V. nRT is a constant because this is isothermal. We take nRT hot out of the integral. We integrate 1 over V dV. That's the logarithm of V, and then we have this equation. This is less than 0 because V2 is greater than V3. So this logarithm is positive, but we have a negative sign here. Therefore, this work is less than 0. What about delta U of this step from 3 to 2? It's isothermal expansion of an ideal gas. Well, because the internal energy of an ideal gas only depends on temperature, delta U is 0. If delta U is 0, Q is delta U minus W, which is just negative W, and we get this expression for Q sub hot. Q is greater than 0 in this isothermal expansion of ideal gas. And similarly, if we look at this step from 1 to 4, it's also isothermal. It also involves ideal gas. It's just this process is compression at a lower temperature. Using similar derivation, we have W cold, which is negative nRT cold, times the natural logarithm of V4 over V1. Because V4 is less than V1, the logarithm is negative, and we have another negative sign here. This work at T cold is greater than 0. Delta U again is 0 for this ideal gas under constant temperature condition, and Q is delta U minus W. In this case, Q is less than 0. So we analyzed these two steps from 3 to 2, isothermal expansion at T hot. From 1 to 4, that's isothermal compression at T cold. Again, T hot is greater than 0. The expression says heat flows from a hot reservoir to the ideal gas. The reason we can keep a constant T hot temperature is because we're assuming our ideal gas is in thermal contact with an infinitely large hot reservoir with this temperature. And now we have this expression of entropy. This is the definition of entropy in thermodynamics. It's an indirect definition. We define the differential of entropy. It's dq reversible over T. So we have dq reversible coming from this, and then we have temperature over here. So delta S hot at this temperature is dq hot over T hot. Because T hot is constant, we can take this T hot out of this integral. Then we have the integral of dq hot. The integral of dq hot is just q hot. Now we have q hot over T hot. We get this expression. Going from here to here. All right, we have this expression for the entropy change of this ideal gas under a constant temperature condition. In this isothermal expansion, temperature is constant, volume increases, entropy increases. Similarly, we have Q cold, and we can derive the entropy change of this isothermal compression. We have this expression: volume decreases and entropy decreases. All right. There is no heat flow in the adiabatic steps. So this is adiabatic expansion. This is adiabatic compression. Both are reversible. So we get this equation. The entropy change of a adiabatic reversible process is 0, only because of the definition of entropy here. If it's a reversible process and dq is 0, ds is equal to 0 over temperature. It's just 0. There's no change in entropy when an ideal gas undergoes this adiabatic and reversible process. And now we will prove this logarithm and this logarithm are opposite to each other. They have the same magnitude and opposite sign. The proof is very simple because we know entropy is a state function, and therefore the cyclic integral of ds should be 0. So the sum of the entropy changes of these 4 steps from 3 to 2, 2 to 1, 1 to 4, 4 to 3, the sum should be 0. And we have entropy change of the isothermal expansion, the entropy change of the isothermal compression, and these two are the adiabatic expansion and compression. The sum is 0. And now by looking at this equation, well, divided by nr, we get this equation. So we have proven the logarithm of v4 over v1 is equal to negative logarithm of v2 over v3. We can remove the logarithms. We can just say, yeah, v4 over v1 is simply the reciprocal of v2 over v3. So you can also say v4 over v1 is v3 over v2. v1 over v4 is simply v2 over v3. And through just simple algebraic operation, we can see this v1 divided by v2 is equal to v4 divided by v3. So we get a lot of equations for the ratios of the volume in this cyclic process. We can prove this same equation using a different way. From 2 to 1, it's adiabatic and reversible. We know the temperature ratio is the volume ratio to the power of 1 minus gamma. From 4 to 3, it's adiabatic and reversible. Therefore, the temperature ratio is the volume ratio to the power of 1 minus gamma. And pay attention here, T1 and T4, they are actually the same. T1 and T4, they are both T cold. Actually, T2 and T3 are the same. They are both T hot. Alright, so we have this equations over here. and also gamma is just Cp over Cv. Now what I will do is I will multiply this right hand side and this right hand side. Okay, so this times this is going to be T1 T3 divided by T2 T4. T1 is T cold, T3 is T hot, T2 is T hot, T4 is T cold. So if you look at this, the result is actually 1. Alright, because T cold cancel, T hot cancel. So this is 1. Therefore, this is 1. Alright, we can combine this 2. And therefore, we have the logarithm of V1, V3 divided by V2, V4. This is just 0. And then, because the logarithm of multiplication is just the addition of logarithms, and we can actually flip this v1 over v4. We can flip this by putting a negative sign here. V2 and v3, we also do the same thing. We put a negative sign here. So mostly it's just from multiplication to addition, and we swap the numerator and denominator by adding a negative sign in front. We have this equation. And then we can move this to the right hand side. We have this equation at the beginning. We have proven this equation. The logarithm of v4 over v1 is equal to negative logarithm of v2 over v3. Also, it means v4 over v1 is equal to the reciprocal of v2 over v3. Alright, so again we have this cyclic Carnot cycle. That means the integral of the cyclic integral of all state functions should be 0. Alright, and we have expressions for S hot and S cold. Alright, so overall the entropy change in the Carnot cycle should be 0. So is the cyclic integral of internal energy, that should be 0. The cyclic integral of enthalpy should be 0. I didn't mention the cyclic integrals of pressure, volume, temperature, but obviously they should be 0 as well, because PVT are also state functions. However, Q and W are path functions. Therefore, it's very likely the cyclic integral of Q is non-zero. Let's look at this. This Q, Carnot, is the cyclic integral of Q. There are 4 steps. We have 1, 2, 3, 4. Adiabatic expansion, Q is greater than 0. Oh, I'm sorry, isothermal expansion, Q is positive. Adiabatic expansion, Q is 0. Isothermal compression, Q is negative, and over here this is adiabatic compression, Q is 0. Alright, and we have this part. This part is actually Q hot. This part is Q cold, and together we have the integral of TdS, and TdS is dq reversible. That's from the definition of ds, and we know this is greater than 0. We have seen the derivation of this part and this part. This part and this part have opposite signs and different magnitude, because this part is proportional to Q hot. This part is proportional to this part is proportional to T hot. This part is proportional to T cold. So this magnitude is greater than this magnitude. So therefore, this Carnot cycle is not going to be 0. And also, we can look at the graphical representation of Q Carnot. If you imagine this integral T hot times TdS, well, it's just the area under this function t with respect to s. So that means we should just make a graph of temperature versus entropy, and we'll do isothermal expansion. Temperature is constant T hot. That's why I have this red arrow with a constant temperature. So going from here to here, and the horizontal axis is entropy. So what's this integral? This integral is just the area under the red curve. So I'm going to draw the rectangle here. So from here to here, and then to here, and then to here, and then to here. So the area of this rectangle is the integral of T hot times ds at T hot. Alright, so this integral. Right, and then let's look at this one, T code, ds code. Well, it's the area from here to here, and then we have this smaller rectangle. Again, this is positive, this is negative, so overall it's going to be this large rectangle minus this small rectangle. The large rectangle minus this small rectangle under the blue arrow is simply the shaded area, and this rectangle has a physical meaning. That's Q sub Carnot. This is the amount of heat of the entire Carnot cycle. Alright, this is just calculus, the integral of this function. The S is just this shaded area. Alright, again, the area under this arrow is simply 0 because the width is 0, same here. So 0 and 0. Now let's get back to the PV diagram. Okay, if we get back to PV diagram, because P external is P, so this cyclic integral of P dV is equal to the cyclic integral of P external dV. So if you look at this shaded area, that's the amount of work. That means the amount of work of this Carnot cycle is not 0. It's equal to this shaded area. Again, over here, this is the integral of PDV from 3 to 2, and down there, the integral, okay, is from 2 to 1. And go back, we need to subtract this area, and then we need to subtract this area. So after you subtract the integral from 3 to 2 and 2 to 1, after you get this integral from 3 to 2 and 2 to 1, it's actually from this line, this vertical line to this vertical line. You get a very large integral area, and then you need to subtract the integral below this 1 to 4 and 4 to 3. So you need to subtract this much. Therefore, the shaded area is the cyclic integral of PDV, which is the cyclic integral of P external dV, which is the amount of work, or the magnitude of work, because over here we do not have that negative sign. In the expression of work, we have work is equal to negative integral of P external dV. So we're going to have a summary over here. In the Carnot cycle, the entropy gain of the system in the isothermal expansion at this temperature cancels its entropy loss in the isothermal compression. Well, because entropy is a state function, so they have to cancel. The cyclic integral of entropy has to be 0. Alright, so we have this equation. And the change of any state function in a cycle should be 0. So we have delta T, delta P, delta V, delta S, delta U, delta H, they're all 0. Later, after we learn Gibbs energy and Helmholtz energy, delta G is 0, delta A is 0. Alright, but Q and W are path functions. So Q of this entire Carnot cycle is not 0, W is not 0. However, Q and W should cancel because we know delta U is 0. So over here we have Q is positive, W is negative, and these two have the same magnitude, and therefore, well, they cancel. This Q of a Carnot cycle and this W of a Carnot cycle should cancel, so that delta U in the end is 0. And overall, the Carnot engine converts heat to work. So if you think about this, Q Carnot is greater than 0, so in each Carnot cycle, heat flows into this Carnot engine, and the W of this Carnot cycle is less than 0. That means this Carnot engine can do work to its surroundings, and overall this Carnot cycle absorbs heat and does work to the surroundings. The heat is converted to work, and the amount of the conversion is this. But don't forget, this Q hot is positive, Q cold is negative. So over here, Q hot plus Q cold, so it's actually less than Q hot. In the Carnot cycle, the system, which is the ideal gas in a Carnot engine, gets heat from a cold hot reservoir. It releases heat to the cold reservoir, but there's a difference. The difference between Q hot and Q cold is the amount of work done by this Carnot engine, and we can have the relation between Q hot and Q cold. Q hot over T hot is equal to Q cold over T cold, and it's equal to this amount of work over T hot minus T cold, and overall we have this is equal to 0. This is only because when we sum up this two, we get the Q Carnot. And the Q Carnot plus W Carnot, it's delta U of the Carnot cycle, which should be 0. Alright, so we have this equation, and then we have this equation. We can then determine the efficiency of this Carnot engine. Overall, this Carnot engine gets heat from hot reservoir, okay, which is this Q hot. And part of the heat is released to the cold reservoir, and the other part is converted to work. So this is greater than 0, okay, and these two arrows are both less than 0. Alright, so one example is this. It's possible for this Q hot to be, for example, 100 joules, and this is, for example, 60 joules, and then only 40 joules of this energy is converted to work. And the efficiency of the Carnot engine is this 40 joules over 100 joules. It's 40%. Alright, it's going to be 40%. Here's the analytical expression. The efficiency of the Carnot engine is denoted by epsilon. Epsilon is the amount of work of the entire Carnot cycle divided by Q hot, and it's just T hot minus T cold over T hot. And we can simplify this. This is 1 minus T cold over T hot. This is always less than 1 because we cannot achieve a 0 T cold. Okay, for us to have this T cold to be exactly 0 Kelvin, it's impossible. So this ratio is always greater than 0 but less than 1. So this epsilon is always less than 1. Alright, the Carnot engine cannot convert heat to work at 100% efficiency. This statement is actually equivalent to the second law of thermodynamics. We can prove this later. We looked at the efficiency of a Carnot cycle, which is this much. Epsilon is the amount of work of the entire Carnot cycle divided by Q hot. It's just this, or 1 minus T cold over T hot. So we got this expression. Epsilon is less than 1. A Carnot cycle cannot convert heat to work at 100% efficiency. And if we look at any other reversible cycle, we can actually express just any reversible cycle as the sum of an infinite number of infinitesimal box-shaped TS temperature versus entropy Carnot cycle. Because if you look at this process, if this process is reversible, we can divide this process into a infinite number of small rectangles. In each rectangle we have a Carnot cycle. So this is isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. And over here we have the cyclic integral of TdS, and this is just the amount of Q in a Carnot cycle. So we can just divide this arbitrary process into an infinite number of rectangles, and the area inside this arbitrary process is equal to the sum of the areas of all those rectangles, and each rectangle is a Carnot cycle, and in each rectangle you have this Q and this W. So again, in the end, just an arbitrary reversible process can be decomposed into a a sum or a combination of just Carnot cycles, and therefore in the end the efficiency of any reversible process should have a efficiency less than 1. Okay, in each of those rectangles the efficiency is less than 1, so overall the efficiency is also less than 1. And again, this Q Carnot of this arbitrary process is simply the sum of the areas of all rectangles in this graph.